Okay, so I'd like to start by thanking the organisers, like everyone else, for the excellent job they've done and giving me a chance to speak. And I'm going to tell you about some joint work with Herb Kamowitz. So here's the abstract, which is almost identical to the abstract that you'll have seen in the booklet, with a couple of minor changes. But so I'm going to be telling you about various kinds of endomorphisms of, commutative Banach algebras, sometimes semi-simple, sometimes uniform algebras, but more generally, commutative Banach algebras in general, and especially semiprime commutative Banach algebras. Let me promise you that the definitions are coming later. Okay. So definitions, as I say, to follow, but what is the sort of definitive result that I've got with Herb on compact endomorphisms, say, of semi-simple commutative Banach algebras and quasicompact, I was going to say here. The nice thing about this one is it's an if and only if, whereas some of the earlier results that, say, Herb got on compact endomorphisms weren't if and only if. This one is a proper characterization of quasicompact endomorphisms, and it's that, particularly looking at the case where you've got connected character space, that's just to make sure there's no non-trivial idempotence, then your an algebra endomorphism of your commutative semi-simple Banach algebra is quasicompact if and only if the powers of the operator actually converge in operator norm to a rank 1 unital endomorphism. So that's pretty strong. And I guess we thought that we'd finished at that point, except that when we looked at the proof, we discovered that we didn't need semi-simple. It turned out that what you really needed was that you didn't have any, the most important thing you needed was that powers of non-zero elements were non-zero. So you have to do a bit of fiddling, and then it turns out that you can move to commutative semi-prime Banach algebras, but the problem there is that, at least if you assume continuum hypothesis, I am assured by Professor Dales that it is possible to have discontinuous endomorphisms of commutative semi-prime Banach algebras. So you actually need to assume continuity before you can get started. But once you've done that, then the theory still goes through, and it actually does work. And then there's a standard procedure you do if your character space isn't connected. I'll tell you something about this, but the standard thing you do if the character space isn't connected, involving decomposition into orthogonal idempotence, and if I've got time, I'll tell you something about that towards the end. So I'm going to tell you something about this and background, and let's get my big red arrow. That should help me to point at things. So I'll tell you something about the background and give you some definitions that you're going to need, and I might even prove something if you're lucky. Okay, so I think by default we expect we're talking about complex Banach algebras here, and most of the time I'll be dealing with unital Banach algebras. And so we've got character space, Gelfand transform. I'll just remind you of some of the standard stuff. And of course, when I say endomorphism here, I mean an algebra endomorphism, so that's a multiplicative linear map from the algebra to itself. And mostly they'll be unitals, so they're going to map the identity element to the identity element. And if you're semi-simple, then endomorphisms are automatically continuous. I say from the early theory, perhaps, gosh, how long ago was it proved that endomorphisms of commutative... Gelfand, okay. So that's early theory. And so then, suppose you are semi-simple, then you can figure out what endomorphisms look like, because they all look like this. They're basically composition operators if what you're composing with is a suitable self-map of the maximal ideal space. That self-map is just the restriction of the adjoint operator to the character space. But if you're not semi-simple, you still get a self-map in exactly the same way by composing with the algebra homomorphism. And so you get the self-map phi, and that's the self-map associated with T. And of course, what you get then is this formula concerning the Gelfand transforms. So it's still like a composition operator using the Gelfand transform, but of course the character space might be rather small and the Gelfand transform might be rather trivial, and so you might not expect to get much information back about the endomorphism from the self-map here. In particular, you're not going to expect to get the endomorphism T back by knowing what the Gelfand, the self-map is. And yet, it still does have applications, as we're going to see, when we're trying to look at which endomorphisms got which properties. So, of course, endomorphisms of a Banach algebra, well, so whatever your objects are, you're going to want to know what the endomorphisms are, because that's the basic thing you're going to look at. So if you're dealing with Banach algebras, you want to know what their endomorphisms are, and you want to be able to find them all. And then you want to know which ones have got additional properties. And so there's a long history about this, which I'm not going to remotely go into, but I will tell you something about results about compact endomorphisms and then the follow-ups from that. And I'll mention also some of the easy things you can do. So in many cases of sort of straightforward algebras, it's completely straightforward to work out exactly what the endomorphisms are and exactly which ones are, say, compact or have got various other properties. So it's sometimes pretty easy. It's quite easy for the disk algebra. It's pretty easy for C of X, things like that. But it turns out even finding out what the endomorphisms are can be tricky if you move to things like Dales-Davy algebras. I won't say too much about that here. I'll tell you in a bit some stuff that is relatively easy, and then some of the stuff that's a bit harder. So as I say, there was quite a lot of work on compact endomorphisms, and then we start to move to these more general conditions that I've mentioned earlier, and some others. And also, you move to wider class of algebras, like semiprime Banach algebras. So I'll just remind you what this means. Well, lots of different equivalent definitions of this. Let's go back to blue. And I don't think I need the arrow anymore. So what does it mean to say a semiprime? So it's a commutative unital Banach algebra. A is semiprime. Sorry? A semiprime if, let's say, no non-zero nilpotent elements, that'll do. But I mean, you can do it with the nil radical, or you can do it with no nilpotent ideal. You can do it by ideals and so on. But for my purposes, what I need is no non-zero nilpotent elements. And so what examples are there? Obviously, semisimple implies semiprime, but not conversely. In fact, there's quite a lot of commutative radical semiprime Banach algebras. like suitable radical Banach algebras of power series and things like that. So plenty of examples around where which are very different from semi-simple. I should say this one you may want to unitize them if you want to get into the unal setting, but certainly they can be very far from semi-simple. So let me say something about some papers on compact endomorphisms, because I want to say stuff that happened a long time before I came into the picture. So we go back to 1978 and then 1980 when Herb Kamowitz did some of the seminal work on compact endomorphisms. So what did Herb do? Well, for a start, he said what are the compact endomorphisms of the disk algebra. So here's the closed unit disk. Here's the disk algebra. So that's the continuous functions on the closed unit disk, so that F is analytic on the open disk. In case you haven't guessed, D is the open disk. And, well, endomorphisms of the disk algebra are pretty easy. You see, you've got this self-map, and you want to know which self-maps give you an endomorphism. So T, an endomorphism of A of D, that corresponds to the self-map from the character space, which is, of course, still the closed disk. So this is a uniform algebra, and that's the character space. That's the self-map. So that's the associated self-map. And of course, you need phi to be actually a map. It's got to be a self-map, but it's also got to be in the disk algebra. So phi itself is continuous on the closed disk and analytic on the interior, and all of those do give you endomorphisms. And so these are precisely the ones that do give you endomorphisms as well. And then T is compact if and only if, well, if and only if either phi of the closed disk, well, it's got to be, it's either it's constant or it's a compact subset of the, let's put it that way. It's got to be constant or it's got to be a compact subset of the open unit disk. Of the open unit disk. So, in which case you can say exactly what the eigenvalues and eigenvectors are and so on. In this case, the iterates of phi, which I'll call phi n, so that's phi composed with phi composed with ... composed with phi n times. Actually, you can ask whether it's been composed with itself n times or n minus 1 times, since there's only n minus 1 compositions in there. But anyway, the nth iterate, phi n, have phi n of the closed unit disk, of course. they converge down to one point, to a unique fixed point of phi, and he also said what the spectrum was, and this is a fairly typical result. So the spectrum of the actual endomorphism is simply 0 and 1 together with all the powers phi prime of, I didn't say what the fixed point was called. Okay, perhaps I should have. Let me redo that. Phi prime of z0 to the n where z0 is the fixed point. And I would say that's a typical spectrum of this type of map result. You get powers of the derivative at the point, and you see that coming back again and again. And if you go up into higher dimensions or even infinite dimensions, you start looking instead at the Riesz derivative and elements of the spectrum of that, and so on. So it's so I would say that's a pretty typical spectrum of a compact endomorphism result. Then, in the next paper, he sort of generalised this iterates down. So then, in the 1980 paper, Kamowitz went the whole hog and proved that if you are if you've got a compact endomorphism of a commutative semisimple Banach algebra, then it's still true that the self-mapped iterates always converge down to a point, a unique fixed point. And this is in the case where the maximum ideal space is connected. So that, let's say, A is what I call a Banach function algebra on its character space. That's just a commutative semisimple Banach algebra, and we'll assume it's unital. And T from A to A is a compact endomorphism with associated self-map phi, then the iterates phi n again, phi n of phi a, again converge down to a unique fixed point of phi. And have I said it? Did I say it was connected? I think I didn't. So that works for all commutative unital semisimple Banach algebras. All Banach function algebras dealt with there. In the case where you're not connected, then the intersection of the images is a finite set instead. And you get sort of attracting fixed cycles and things like that. Okay. So then Klein generalized this significantly but only in the case of uniform algebras. So what Klein did was he proved that in the first setting with a connected maximum ideal space for uniform algebras, what happened was he actually showed that the operators, the powers of the operators, converge to a rank 1 endomorphism in operator norm, which is one of the things I was already mentioning earlier. So Klein got that result. So he looked at the convergence of t to the n to a rank 1 endomorphism, which wasn't there in the Kamowitz paper, and got some very nice, neat proofs that only work in the uniform algebra setting. As far as I can tell, most of them don't go through. No, let's move on because it's taken me longer than I thought. So let me not take too long over this definition then. What's the essential spectral radius? You probably are familiar with the Calculus algebra, so you take the bounded operators, quotient by the compact operators, and then you can take the spectral radius in there, and you get the essential spectral radius. And Riesz operator means your essential spectral radius is 0, while quasicompact means, for us, essential spectral radius less than 1. That's not the only definition of quasicompact around, but there's more than one definition of quasicompact around. They usually coincide for endomorphisms, but since some people say that that's the same as power compact, I don't mean that kind. Power compact is something different, and so what you get is compact implies power compact, implies Riesz, implies quasicompact, but converses are false, even for uniform algebras, and I'm not going to have time to show you those examples here. So let me just move on to tell you what are the results we've got then in a completely general setting. So you've got your associated self-map and so on then. So here's the one I mentioned earlier. You're quasicompact if and only if the operators t to the n, they converge in operator norm to a rank 1 uniform endomorphism. And the rank 1 uniform endomorphism, of course, that corresponds to the unique fixed point of your self-map. And then it works again, because what you really, the most important thing you needed was that powers of eigenvalues were still eigenvalues. And a few other little fiddly tricks, and then you find it works for commutative semiprime Banach Algebras as well, as long as the character space is connected. If the character space isn't connected, then here's what you do. You use a standard decomposition into idempotence trick that I'm not going to have time to tell you, unless you want to see it. And then again, you get the finitely many attracting fixed cycles that Klein got in his big thesis, and which is reflected when you look at the operator by saying the sum power of the operator whose powers converge. So it's a very nice subsequence of the powers, which corresponds to these attracting fixed cycles. And these t to the kn's as k vary converge an operator norm to a finite rank endomorphism. And that generalizes this earlier work. And I just wanted to flash past a few questions. Sorry if I've gone a couple of minutes over, but here are lots of things you can do. You can find the endomorphisms, the compact endomorphisms, the quasi-compact endomorphisms. Quite a few people are doing this now, including one of my research students. Then you can look at semiprime Banach algebras. These are completely open-ended things because there's no end to the algebras you can look at, the classes of operators you can look at, and so on. So you can do as much or as little of this as you want. Finding the spectra, if you don't assume quite strong conditions on the operator, seems to be a bit hard. Finding the spectra of a general endomorphism, I think, is a bit of a tough order, but maybe the experts on operator theory can do that. And then I won't have time to tell you much about these other ones, but you can tell me which class of operators you think we should look at next, and whether there's non-commutative versions of all this stuff. But I think I should stop there.
Do we have a question? I think not. Thank you very much, Joel. Please stay seated for a moment.